Okay, let's move to the chapter number 4, probability. Probability, okay. Okay. The chapter 4.1 is about empirical probability, and chapter 4.2 that is theoretical probability. 4.3 conditional probability and counting techniques. Let's move to the chapter 4.1. Empirical probability. Okay, let's check. Personally, I think the chapter number 4, the importance is fair, just fair. But chapter number 3, number 5 are very, very, very important. Okay. Okay. Definition 4.1.1: experiment. Experiment, an activity that has specific result that can occur, but it's unknown which result will occur. Okay. Specific result that can occur, but it is unknown which result will occur. Outcomes, the definition of this term, outcomes, the result of an experiment. Experiment, okay. Event, a set of certain outcomes of an experiment that you want to have happen. Event, a set of certain outcomes of an experiment that you want to have happen. Okay. Definition, sample space, collections all possible outcomes of an experiment, and use the abbreviation SS, double S, okay, sample space, okay, and event space, a set of outcomes that make up an event. The symbol usually use capital letter, ES, okay, and let's check here. Trials of die experiment, and if we roll a die for 10 times, the number of 6, it appears twice, and the relative frequency is 0.2. If we roll a die 50 times, the number of 6, appearance of 6 times, the relative frequency would be 0.12. If we have chance to roll a die for 1,000 times, and the 6 comes 163 times, and the relative frequency would be 0.163. And here, experimental probability, the probability is the number of times of A occurs, and the number of times that experiment was repeated. For example, if I throw a die for 1,000 times, and I focus on the number 6. The number 6, it appears 163 times, and the probability will be 0.163. That is based on experiments. Again, that is based on experiment. If the die is a fair die, and the 1 point, 2 points, 3 points from 6 points, theoretically, the probability to come any one is equal. And the theory, if we throw 1,000 times, divided by 6, that would be 6 point, very close to this number. That is a theoretical probability. But according to the case here, that is based on experiments. Sure, sometimes the experiment results very close to the theoretical results. Why? Because the dice is fair. But if the number 6 or number 5, the structure of the die is different. Structure different. For example, okay, the dice. Okay, if the structure, for example, the number 5, maybe the weight center is close to down, and the number 5 will appear more frequently. It's not a fair die. It's not a fair die. But if the die is a fair die, we can throw it for many times and accumulate enough time, 6 points the appearance with a similar frequency. We call it a theoretical frequency. Okay, and let's check. Let's come back. Law of large numbers. Law of large numbers. As n the experimental times increases, the relative frequency trends toward an actual probability value. When we increase the experiment numbers, the relative frequency trends towards the actual probability number, the value, okay? As homework here, example 4.1.2 contains the number of mm's of each color that was found in a cast, and find the probability choosing each color based on this experiment. What's M and M? a chocolate with a sugar coating, right? Actually, I was a M chocolate lover, but not now because I'm getting old and I need to take care about my health. Okay, and there are brown, blue, brown, green, orange, red, or yellow, and the total chocolate sugar is 26, 20, and find the probability choosing each color based on the experiment. 481, 371, 483, like this one. So we can calculate the probability that is based on the experiment. But you can say, oh wow, $1. I observed 1, 2, 3, 4, 5, 6 colors. Theoretically, they should have the same probability to be chosen. Maybe kids they love different colors, but the average should be. No, I personally, maybe I love blue chocolate MM. Maybe someone like brown, like this one. So it's kind of consumer evaluation or food testing. Food evaluation, we will do it close to the end of the semester. I think I will get a budget very soon. We can do something different, okay? Like this one. Okay, let's move. Okay, let's move to the second one. Chapter 3, 4.2, theoretical probability. It's not always feasible to conduct experiments over and over again. Thus, it would be better to be able to find the probabilities without conducting the experiment. And those probabilities are called theoretical probabilities, okay? To be able to do theoretical probabilities, there is assumption that you need to consider is that all the outcomes in the sample space need to be equally likely outcomes. Again, equally likely outcomes. And this means every outcome of the experiment needs to have the same chance to happening. Okay, example, which of the following experiments have equal likely outcomes? First one, rolling a fair die. Second one, flip a coin that is weighted so one side comes up more often than the other side. Okay, then pour a bowl out of a can, contains 6 red balls and 8 green balls, and all balls are the same size, maybe the same the material. Picking up a card from a deck, rolling a die to see if it is fair. Okay, let's move. The formula here: theoretical probabilities if the outcome of experiments are equally likely, then the probability of event A happening is the denominator is outcome in sample space. All possible outcomes, you can place the sample in the denominator. How about the numerator? Outcomes in spatial event. For example, event A. Okay, and suppose you conduct an experiment where you flip a fair coin twice. What is the sample space? Head, tail, tail, head, head, tail, tail. There are, you can say 4 combinations or 3 combinations. You can think different. Okay, what is the probability of getting exact 1 head? What is the probability of getting at least 1 head? At least 1, what does it mean? The sample space, we can check. Sample space, head, tail, tail, head, and tail, tail. Thus, if A getting exactly 1 head, the event will be the sample space in the denominator. 4 events: head, tail, tail, head, and tail, tail. Okay, and according to the question number B, exactly 1 head, 2 events. So sorry, two sample, head, tail, tail, head. Thus, the probability, theoretical probability, is 2/4. That's 50%. Okay, just one more. Getting at least 1 head. At least 1 head, we can find the sample space here. Head, yes. Head, tail, yes. Tail, head, yes. Tail, tail, no. Okay, so there are 3 outcomes, and the 3 outcomes fit the criteria of the question number C. Thus, the probability is 3/4. Okay, I think I can stop here. About this one. I think the card is complicated. We can ignore this part. Okay, and check chapter 4.3. Again, personally, I don't think the chapter number 4 is important. Thus, I will skip it most. Okay, and here, conditional probability are probability calculated after information is given. Again, what is the title? Conditional probability. What's the definition? That probability calculated after information given, and sometimes it's called a restricted sample space. Okay. Suppose you roll 2 dice. That is probability of getting a sum of 5 if the first die is 2. Suppose you roll 2 dice, okay? Then what is the probability to get a sum of 5 given the first die? When the first die is 2, you have no choice. The second die must be 3. But the second die has here. The second die has 1, 2, 3, 4, 5, 6 possibilities, 6 outcomes, and when the first die has been restricted as number 2, and the outcome to 1, to 2, to 3, to 4, to 5, to 6, there are 6 possible outcomes here, And outcome restricted sample space, the way to get a sum of 5 is only 1, 2, 3. Thus, the probability is 1/6. 1/6. So far, any question? Okay, let's move. Question: independent events. What does it mean? What does it mean? In this case, knowing that the first die is 2, they change the probability of getting a sum of 5. In the first case, the events sum of 7 and the first die is 4 are called independent events. Independent events. In the second case, the events of sum of 5 and the first die is 2 are called dependent events. Dependent events. Okay. Events A and B are considered independent events if the factor that one event happens does not change the probability of the order. Again, one event happens does not change the probability of the other event happening. In other words, event A and B are independent if the fact of A has happened does not affect the probability event of A. Okay, then the fact of A has happened does not affect the probability of event B happening. Otherwise, the two events are dependent. One happened, they will change the second event. They will affect the second event. That is called dependent. But the two events, they are independent. We call independent events. Okay, then let's check the example. Suppose you roll 2 dice. Are the events sum of 7 and the first die is 3 independent? Let's check. To determine if they are independent, you need to check if the probability A based on B equals probability of A. It doesn't matter. It doesn't matter which event is A or B. Just assign one as A and one as B. Let A equals sum of 7, and there are some combinations: 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, and 6, 1. There are 6 combinations of this. And B, the first die is 3. The first die is 3. The first die is 3, then the second die could be 1, 2, 3, 4, 5, 6. 6. And probability A based on B means that you assume the B has happened, then the restricted sample space is B. The restricted sample here R equals 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6. In this restricted sample space, the way for A to happen is 2, 4, because the sum is 7. Okay, so the probability A based on B, that is 1/6. And the probability A is 6/36, 1/6. Thus, the probability are the same. We call the sum of 7 and the first die is 3 are independent. You will not affect my happening. I will not affect you. We call them independent. Okay, that's done. That's done. Multiplication. Okay, I think we can skip this one. Okay, this one. Multiplication rules. 2 more useful formulas. If 2 events are dependent, then probability A and B equals probability A times probability B based on A. If 2 events are independent, like this one, if you solve the first equation for this one, you obtain probability B over A, P based on A like this one. Which formula to calculate the conditional probability? However, it's easier to find the conditional probability. Okay, let's check the first. Suppose you pick up 3 cards from a deck. What is the probability they are all queens if the cards are not replaced after they are picked? Just pick up, then we not put it back. So 1, we can see that. For the first time, the cards there are 52 cards, 50 cards from ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, and king. So on this condition, what's the probability to pick up question? All pick up 3 cards and 3 cards are all queens. What's the probability? For the first formula here, 52, the total number of cards, and 4 cards are queens. The probability is 4 over 52. After, sure, the events, you get 1 queen, and the total number of the card becomes 51. And the remaining cards of queen is 3. Thus, multiply 3 over 51. Again, after 2 queens cards has been drawn, the total number is 50, and the remaining number of queen is 2. Thus, we can calculate this one. We get 24 over 13 hundreds, like this one. Is it okay? Is it okay? Okay, let's move. This one, I think I can skip this one. Okay, this one. And okay, let's move to chapter number 4.4. And there are times your sample space or events are very large and it's not feasible to write down. In this case, it helps to have mathematical tools for counting the size of the sample space and event space. These tools are known as counting techniques. Okay, definition: multiplication rules in counting techniques. If text A can be done M1 ways, text 2 can be done in M2 ways. So for to the task N being done Mn ways, the number of ways to do task 1, 2, 3, 4 until N together will be M1 multiply M2 multiply until Mn. Okay. Like this one, multiplication rules in counting. Menu offers a choice of 3 salads, 8 main dishes, and 5 desserts. How many different meals consist of 1 salad, 1 main dish, and 1 dessert are possible? It's a kind of calculate population, the combination. Solution: there are 3 tasks: pick up a salad, a main dish, and a dessert. The salad task can be done in 3 ways, and the main dish has 8 in 8 ways, and the dessert task in 5 ways. Thus, the combinations is 3 times 8 times 5. The combination will be 120 different meals. 120 different meals. Okay, so far any question? Okay. Like this one. Okay, and I think I can stop here, and next week we can start from the chapter number 5. Okay, and chapter number 5 here, the importance is fair to close to important. Okay, I think I will stop. Give any instruction here. Any question, please let me know. And you can review the calculation, the standard deviation. You can calculate the percentile.